Welcome everyone to this special session of the colloquium. Bonjour tout le monde, bienvenue à cette édition spéciale du colloque. Today we have the pleasure of having Tristan Collins, who will speak about his research for the prize that he received, that is the André-Aisenstadt Prize. And this prize was created in 1992, and it is one of the flagship prize programme at CRM. Nous sommes très heureux d'accueillir Tristan Collins pour son exposé pour le prix André-Aisenstadt. This year, the prize was received ex aequo with also Giulio Tiozzo. And this is a prize which recognizes talented young mathematicians in both pure and applied mathematics. So Tristan Collins is an assistant professor at MIT. Before that, he was a Benjamin Peirce assistant professor at Harvard. He did his PhD at uni with D.H. Fung, and he's been at UBC for a while before that, working with Malabika Pramanik. His field of research is between geometry and analysis, and in particular, he's interested in algebraic geometry applied to analysis and vice versa. And he's supported by among many other sources, an Alfred Fellowship. And today, he will speak about exploring string vacua through geometric transitions. Tristan, the stage is yours.
Okay, thank you very much. Obviously, it's a huge honor for me to give this talk. So I'm going to try to explain some recent work of mine in collaboration with some other people who I'll mention along the way, but I also want to just describe a sort of general set of problems which are sort of motivated by problems that arise in string theory. So the plan for the talk is to explain a little bit about string vacua. So I should emphasize that I am not a string theorist. But I am going to just try to explain some of the more concrete mathematical aspects of string vacua, which will play a role in this talk. And then I want to talk in particular about the heterotic string in Calabi-Yau manifold. So the heterotic string is one of these examples that I'm going to focus quite a lot on throughout the talk. And then I want to discuss geometric transitions and a problem in what could be thought of as complex algebraic geometry or complex differential geometry called Reed's fantasy, and it's sort of connections with this string vacuum degeneracy problem. And then I want to discuss how these geometric transitions play a role in various aspects of string theory, so both for the heterotic string and for type 2a and B theories, and this is really where I'll discuss my research. So let me begin by reminding you that so what is string theory? Well, it's some physical theory which is an attempt to try to unite the sort of the theories of electromagnetism and weak and strong interactions, which we understand as gauge theories, with general relativity, which is of course a theory of gravity of differential geometry. So this was initiated sometime in the late 70s, and it's generated a huge amount of interest, both in mathematics and physics. It's really spun off a lot of very beautiful mathematics. So there are essentially 4 types of string theory, which live in 10 dimensions. There's type 1, type 2a, type 2b, and heterotic string theory. So these are all supposed to be some limits of something which lives in 11 dimensions called M theory, but I'm not going to talk about M theory because I'm not a physicist. And I'm really only going to talk about the last 3 examples, so type 2a and type 2b and the heterotic string. So probably the most familiar examples of string theories, or the kind that mathematicians interact with most commonly, are the type 2a and type 2b theories, because these are really the theories that give rise to mirror symmetry. So these theories have given rise to things like the Fukaya category, homological mirror symmetry, and things that a lot of mathematicians are working on, which are sort of rigorous, well-posed mathematical problems. So roughly speaking, type 2A is a theory of symplectic geometry, while type 2B is a theory of complex geometry. So that's very rough because, of course, there's no such clean distinction. But for the purposes of this colloquium, we can take that as some sort of slogan. And the heterotic string is really a theory that happens or appears in sort of complex geometry or maybe generalized complex geometry. And you can think of it roughly as a theory which is coupled to vector bundles. So, so let me explain a little bit about why these objects or these ideas that come from string theory really give rise to problems in geometric analysis. So each of these theories gives rise to a background geometry, which is a 10-dimensional space. And usually in practice, one takes this space to be a Lorentzian space, the usual R31 or R13, depending on conventions, crossed with a Riemannian manifold of dimension 6. And this Riemannian manifold is often taken to be compact. So this is what people often refer to as the small or internal space. So this is the space that we cannot enter. But this 6-dimensional compact Riemannian manifold comes equipped with a bunch of geometric structures, which depend on which theory you're considering. So, for example, in type 2A theory, M would come with a symplectic form, or in type 2B theory, M would come with a complex structure. So this internal space comes with a whole bunch of extra structure dictated by your theory. And these structures aren't just sort of random. They're actually specified to satisfy a system of usually highly non-trivial nonlinear partial differential equations. And when we talk about the vacuum, we're really talking about so for the purposes of this talk, we'll be talking about a 6-dimensional compact Riemannian manifold with a set of geometric structures which solves these differential equations. And so that's what we mean by a vacuum. So a well-posed mathematical problem is to say, well, suppose you have a compact Riemannian manifold of dimension 6, or just say compact 6-dimensional manifold. When does it admit solutions to these string vacuum equations of motion? So that's a very well-posed problem in geometric analysis. And this question already leads directly to deep and interesting mathematics. And so I'd like to highlight this by explaining or briefly recalling this famous work of Candelas, Horowitz, Strominger, and Witten, which I'll from now on refer to as CHSW. Oh, so by the way, just stop me if there are any questions. So, so what did CHSW do? Well, they found solutions to the vacuum equations of motion for the heterotic string in the case of what's called zero flux. And I'll try to explain what zero flux is in a moment. It's quite concrete. So let me say what they did. So, so after the work of CHSW, Strominger and independently Hall derived the equations of motion for the heterotic string possibly with flux. So it's a slightly more general setting. And so I want to, so these equations are called the Hall-Strominger system, and they're going to play a pretty fundamental role in this talk. So I'm going to spend some time explaining where these equations, or what these equations are. I won't explain where they come from. So the first piece of structure that this manifold has to have is a complex structure. So in particular, it has an endomorphism of the tangent space, which squares to 1, and which is integrable. So let me give a more concrete definition of this. So M is a complex manifold. So I'm going to just alternate between my slides and this drawing. So here's M. And typically, to be a manifold, one would require that you can cover M by local coordinate charts, which are maps to Rn usually. So we have these local coordinate charts. But to be a complex manifold, we require that these maps are instead valued so in this case it would be C3. So they have complex coordinates, Z1, Z2, Z3. And you can do this again on this other coordinate patch. So you have this little local map to C3. So you have these complex coordinates. And this is in C3. And to be a complex manifold just means that you can do this in such a way that when you change coordinates here, you get a map from C3 to C3. This is supposed to be holomorphic. Okay, so this is what it means to be a complex manifold, just that you can cover your space by local coordinate charts with holomorphic transition functions. So you can imagine that this complex manifold is just locally modeled on C3. So the next requirement is that M must admit a global non-vanishing holomorphic 3-0 form. So what does that mean? Well, that just means that when I look in these, there's some global object, which I'm going to call omega, which anytime I write in local coordinates, it's of the form f of z times dz1 wedge dz2 wedge dz3. So here f of z is some holomorphic and non-vanishing function. And you can see already that this is well defined, because when I change coordinates, of course, this is just going to transform by the determinant of my holomorphic transition function, which is going to preserve the fact that f of z is holomorphic and non-vanishing. So one requires that you have a global section of this complex line bundle, which is going to be called omega, and it's nowhere vanishing. So such manifolds are often called Calabi-Yau. Well, I'm going to call them Calabi-Yau for the purposes of this talk. So secondly, M comes equipped with a Riemannian metric, G, which is Hermitian. So it's invariant under the multiplication by the complex structure. And so this is the sort of background data that comes automatically from. So this is the sort of input that one needs to even state what this Hall-Strominger system is, but it comes directly from the string theory that these structures exist. And then there's a holomorphic vector bundle, which is just a complex vector bundle, again with holomorphic transition functions, and it has a Hermitian metric H. So this is the background data, and these data are required to satisfy a system of partial differential equations, which I'll now write down. So we can introduce this form omega, where you just put a complex structure in one of the slots of the metric. So this is a 2 form, because G is Hermitian, it's antisymmetric. And then we ask that omega and omega G, H, J satisfy this the following set of equations. So there's a conformally balanced equation. So I take omega and I wedge it with itself, and I multiply by the norm of the holomorphic volume form, which is this ratio defined over here. Well, I define the square of it. And then that is supposed to be declosed. So that's one equation. There's a Hermitian-Yang-Mills equation. So I take the curvature of the unitary Chern connection on E. And if I wedge it, so that's a 2 form valued in the endomorphisms of E. If I wedge it with omega squared, that's a 3 form, or sorry, a 3 form. So it's a 6 form, and that's required to be 0. And then there's a very complicated looking equation, which is called the anomaly cancellation equation, which says that if I take the complex Hessian of omega, so I dd bar, then this should be equal to some positive multiple of the trace of the Riemann curvature of G wedged with itself, minus the trace of the curvature of E wedged with itself. So this is a very complicated equation. It involves, well, it's quite complicated. It's quadratic in the curvature of both the metrics H and G. So this is, in some sense, the most intimidating of these 3 equations. Okay, so so what did Candelas, Horowitz, Strominger, and Witten do? They found solutions to this. In fact, they found many solutions to this this very complicated system. And how did they do that? Well, they started by imposing an ansatz, which is that omega is D-closed. So in particular, this makes omega a symplectic form and means that we're firmly in the realm of what's called Kähler geometry. Okay, so what does this do? This, as soon as d omega is 0, well, it automatically implies that I dd bar omega is 0. Now we can also take this extraneous vector bundle, or this extra piece of data, to just be the holomorphic tangent bundle. So the holomorphic tangent bundle is just the span of the differentials associated to the holomorphic coordinates. And then this bundle has a natural metric, which is just to take the metric h to be the metric g, which is already defined on the tangent bundle. So the upshot of this is that if we come back to our Strominger system, you see we've taken IDD bar omega is 0. Okay, so we get a 0 here. But now G and H are the same. So the same in this CHSW ansatz. These are the same. So in particular, this is just automatically equal to 0. So by this ansatz, you see we just kill this intimidating anomaly cancellation equation, and it leaves us just with the first two equations, but with the understanding that now H is supposed to be equal to G. So somehow this looks like an overdetermined system because this G has to solve two equations at once. But actually, it turns out that is not an overdetermined system. So we kill the anomaly cancellation equation. What does the first equation become? Well, we go back to our holomorphic, or our anomaly cancel, or our Hall-Strominger system. When you take D here, you distribute this in, this guy is going to automatically die because d omega is 0. So all you get out of this equation is that the derivative of this norm is 0, which means that this is a constant. The norm of this holomorphic volume form is a constant. And this is, you can write this as an equation, which says that if you take the symplectic form and you cube it, so that's, in other words, the Riemannian volume form, it's equal to omega wedged with omega bar up to a constant. Okay, so this is called the complex Magen-Peir equation. And actually, if you solve this equation, then you're automatically Ricci flat. So there's 0 Ricci curvature. And actually, this automatically implies that the second equation, this Hermitian-Yang-Mills equation, holds, because in this case, this is actually equal to the Ricci curvature. This would be equal to the Ricci curvature, maybe times the volume form, up to a factor. And this would be 0 because G is Ricci flat from the complex Magen-Peir equation. So what this ansatz has done is it's reduced this complicated Hall-Strominger system to a single equation, which is the complex Magen-Peir equation. Okay, so this CHSW ansatz reduces this problem of finding heterotic string vacua with 0 flux to the problem of solving the complex Magen-Peir equation on a compact Kähler manifold that has this extra property of having a non-vanishing holomorphic 3-0 form. So luckily for Candelas, Horowitz, Strominger, and Witten, 7 years before their work, Yao had proved that this was always possible. So if you have a compact Kähler manifold with this, in fact, even weaker condition, just that the first Chern class is 0, so that's implied by this non-existence of a non-vanishing holomorphic tree form, then there's always a unique solution of the complex Majorana-Pair equation in any cohomology class which supports a Kähler form. So in fact, this produces on a general Kähler manifold with trivial canonical bundle, this produces many solutions, one for every cohomology class which contains a Kähler form. So of course, this is a famous work which was recognized with the Fields Medal, but in particular, it turns out that this Hall-Strominger system can be viewed in some sense as a generalization of this complex Majorana-Pair equation to a sort of more general setting. So it's a system which contains a complex Majorana-Pair equation as a sort of special case. Now, actually, it turns out that these compact Kähler manifolds with non-vanishing holomorphic three forms are actually relatively easy to cook up. So, for example, if you take a quintic polynomial in complex projective space P4, for example, just to be explicit, so e.g., you take this zero set of this polynomial inside of the complex projective space P4. This will have the required properties, and so in particular gives rise to a solution of these of this Hall-Strominger system. So in particular, this theorem of Yau yields a huge number of solutions to these heterotic string vacuum equations. So that's well, okay. Let me also remark that in fact that these solutions of Yau actually also provide solutions to the vacuum equations for type 2a and type 2b, which I haven't said what those equations are, but let me not worry about that for now. Okay, so this is in some sense good news because these CHSW solutions yield a huge number of distinct possibilities. So that gives you some freedom to try to engineer your theory to look like the observable universe. On the other hand, oh yeah, right. Let me just mention. So if we drop the fact, so what does it mean to have zero flux? It's just that this d omega is zero. So if we drop that assumption, then actually the existence of solutions to the Hall-Strominger system with flux, this is an area that's generating a lot of interest, but actually there's no general existence theorem known. So this question about when there are solutions and when there are not is totally open. And in fact, I think it's even we're only sort of currently learning how to even properly phrase such a general, how one might even state such a general existence theorem, let alone prove it. So this is a very interesting active area of study. So in particular, we have all of these many solutions to this Hall-Strominger system, but actually physically this is in some sense problematic. So why is it problematic? Well, if you believe that some string theory was supposed to be a model for the universe, but on the other hand, there are sort of many distinct, geometrically distinct solutions of these string vacuum equations, then you somehow need to decide which vacuum is supposed to be the correct model. So, for example, this makes using string theory to make predictions quite difficult because there are so many different models. It's not clear which one should really be the right model, and therefore it's hard to decide which example you should be trying to make predictions out of. So this looks like bad news for string theory, but a possible resolution to this paradox, it was proposed by several people in the 80s, both in sort of physics and mathematics. well, from different angles. But the proposal is that actually all of these different vacua, these different solutions of the string vacuum equation are actually connected. And they can't be connected by any sort of nice, smooth transitions, because these Calabi-Yau manifolds, or these solutions that Yau produced, can be distinct topologically. So they have to be connected by something which is rather a sort of singular transition, which I'm going to call geometric transitions. So let me draw. So this, in mathematics, this is a striking conjecture which is known mathematically as Reed's fantasy. So let me try to draw this picture. So you start with some Calabi-Yau, say it could be this quintic example. And then the idea is that maybe if you have a different theory, which lives on a maybe totally distinct Calabi-Yau manifold, then there's supposed to be some sequence of transitions which allows you to join these two. So these are supposed to be, these are geometric transitions. And that actually all solutions of these string vacuum equations should fit into this big web. So you can imagine this looking like a spider web, where somehow every two solutions can be joined by some sequence of these. So maybe there's some solution over here, and to get there, you have to go this way and then this way. You can go, I mean, these arrows are a little bit misleading. You can go either way along these arrows. So that's the proposal. So let me explain what this conjecture, well, maybe I should not call it a conjecture, this fantasy is proposing. So we start with one of these Calabi-Yau manifolds, and let's suppose that it has a special curve that lives inside it called a -1, rational curve. So what is this? This is just a holomorphic curve. So it's cut out locally by holomorphic equations, or by polynomials, say, by complex polynomials, which is supposed to be globally just a sphere, so S2, think of it as CP1. So it lives inside of M, and its holomorphic normal bundle is supposed to be two copies of this tautological bundle. So a direct sum of -1 with itself. So these curves are quite special because they're sort of rigid. They don't move at all. And as part of the sort of consequence of this rigidity, it turns out that a neighborhood of C is actually the same holomorphically as a neighborhood of the zero section in this total bundle, or in this normal bundle. So it turns out that there's a map which sends this total space of this bundle to an affine variety. And what it does is it sends this zero section, so this P1, I'll draw a picture of this in a second, it sends this P1 to a point, but everywhere else it's sort of a perfectly well-defined, very nice map. So what it does is contract this zero section. So let me draw a picture. So you start with so this is going to be a kind of funny picture. So this is an S2, CP1, and it has a rank 2 vector bundle over it, complex vector bundle. Something like this. Oh, -1, direct sum twice. And now there's a map. Don't use that, use red. So there's a map which sends this to a space that looks like a cone. So it's just the zero set of this polynomial, sum from I equals 1 up to 4, ci squared is 0. And this entire P1, this rational curve, is mapped to a point. So that is, so it's singular, this space is singular. But the singularity is an isolated singularity, and it's exactly the image of this P1, and everywhere else is sort of, we have a perfectly nice, well-defined map. Okay, so this is this is called a well, the inverse map of this would be called a small resolution. And this V0 is called the conifold. So it's got an isolated singular point at the origin, and it's it looks like a cone. So it turns out that, well, it's not so hard to see that this conifold has a natural smoothing where you just take this, what was formerly 0 on the right-hand side and just make that be a variable called t. And it turns out that as long as t is not 0, these affine varieties are now smooth. And in fact, they're diffeomorphic to the cotangent bundle of S3. So in other words, I'll go back to my picture. So there's a family of varieties, affine varieties, which look something like this. So this is for t not equal to 0. Maybe as they get closer, they maybe get a little bit pointier, but they're still nice and smooth. And then at t equals 0, they inherit a singularity at this one point. Okay, so these are these. This is total space. VTs, which are perfectly smooth, and then we have V0, which is the conifold. These guys are perfectly nice and smooth. Okay, so this is and these manifolds are diffeomorphic to the cotangent bundle of S3. So this is called a conifold transition, this process. So what I do, I just sort of combine these processes to get a conifold transition. I start with something which is a vector bundle over P1, which is again smooth. I do this contraction map to the conifold. Contract P1, and then I do a smoothing, which I denote by this squiggly arrow to get this smoothed out thing. This is one of these VTs. I think this is O minus 1. Copies. Okay, so this is quite a violent transition topologically, because you see under this map, we have this P1, which is deleted, right? P1, which is an S2. So this map deletes an S2. And this map introduces an S3, which is exactly the 0 set, which is the 0 section inside of the cotangent bundle of T star S3. So this is quite a violent operation topologically. I'm removing a 2-sphere and introducing a 3-sphere. So this is the local model for a conifold transition, and it's a topology changing transition. So the reason this is good news is that at least for this local model, this gives us a way to try to move between Calabi-Yau manifolds, which are different topologically. So this is so this looks like good news from the point of view of understanding how to connect Calabi-Yaus. And what so well-known work of Friedman showed that actually these local, so this is just a local model. Of course, you could say, well, maybe this never actually happens in any real compact Calabi-Yau. But Friedman showed that in fact it does. So if you have simply connected Kähler Calabi-Yau manifold, some collection of these -1 rational curves, and they satisfy a linear relation in the second, sorry, this should be homology group. Then there is a conifold transition. So you can contract all of these spheres, and then you can smooth out the resulting singularities. And this process of contracting the spheres and smoothing out the singularities is actually, it actually preserves the property of being Calabi-Yau. Although it can certainly pass from being Kähler to being non-Kähler. Okay, so what's Reed's fantasy? Well, Reed's fantasy is that by doing this, we can join all possible simply connected Calabi-Yau manifolds of real dimension 6. So that these arrows, these geometric transitions that I was explaining, you could, if you give me any two Calabi-Yau manifolds, I could go from one to the other by a process of either contracting. So of course I can do this process also in reverse. I could contract an S3 and then take a small resolution. So that's the sort of backwards geometric transition. So by doing those in some order, I can get from one simply connected Calabi-Yau to another. There are more general versions of geometric transitions where you can contract stuff that gives you singularities other than the conifold. And as long as they're smoothable, then those you could also allow a sort of more general version of these conifold transitions. But I think the sort of generic case is the conifold transition case. So I'm going to focus on these conifold transitions. So there's some experimental evidence for Reed's fantasy. So primarily for complete intersection Calabi-Yaus, people have checked that actually in this big moduli space of Calabi-Yaus, you can join tons and tons of examples together by these conifold transitions. But this evidence, I mean, despite the fact that there is some experimental evidence and not just a small amount, it's by no means enough to promote this fantasy to a conjecture. So why is this conjecture so difficult? Part of the difficulty is that so what can happen is actually when you do this conifold transition, you can kill all of the second cohomology. So there are examples where the cohomology is in fact generated by degree 2 part of cohomology is generated by these rational curves. And when you do these contractions, you actually lose all the H2. So of course, a Kähler form defines a non-trivial element of H2, and that allows you, so that means that these conifold transitions, you can certainly pass outside of the Kähler realm. And why is that bad news? Well, Kähler Calabi-Yau manifolds, we have some tools for understanding them because we have Yau's theorem, which you can think of as a sort of uniformization theorem. So it's a very useful tool in trying to understand the Kähler Calabi-Yau manifolds. But for non-Kähler Calabi-Yau manifolds, we don't really understand them as well because we don't have a version of Yau's theorem. There's no sort of uniformization type result. And so a proposal which has been advocated by Yau for some time is that that actually we should view this Hall-Strominger system as playing the role of the complex Monge-Ampere equation for non-Kähler Calabi-Yau manifolds. And actually that it may be the right way to uniformize non-Kähler Calabi-Yau manifolds, and it may actually help us to understand this Reed's fantasy. So this means that both if we want to understand this sort of mathematically well-posed problem of understanding Reed's fantasy, or just in general understanding non-Kähler Calabi-Yau manifolds, or if we want to understand this vacuum degeneracy problem, the fact that we have all these different solutions to the heterotic string vacuum equations, then both of those questions lead to the same sort of problem, which is, for example, suppose you have a conifold transition where you start with a Kähler Calabi-Yau manifold M, then can you pass solutions of the Hall-Strominger system through this conifold transition? So let me explain why this would be relevant for the physics side. So from the mathematics side, it's just a question of whether we can uniformize Calabi-Yaus which are connected to Kähler Calabi-Yaus by conifold transitions. But on the other hand, on the physics side, let's even suppose we knew Reed's fantasy. Suppose you have some collection of Calabi-Yaus which are joined by some sequence of conifold transitions, or or their inverses. Even assuming Reed's fantasy, if we knew somehow that these two had solutions of these two solve the Hall-Strominger system, and these two solve the Hall-Strominger system, but we don't know that we can pass solutions through conifold transitions, then it might be the case that this one does not. And so even though the moduli space of Calabi-Yao's is connected, if the moduli space of solutions is not, we still don't sort of resolve this vacuum degeneracy problem. So you can view this, I mean, you can view this question as attempting to make progress on sort of both of these things at the same time. Both Reed's fantasy and this vacuum degeneracy problem. Okay, so this question of solving the Hall-Strominger system through conifold transitions has generated quite a bit of interest lately. So let me try to explain why this should be a tractable problem. So recall that so this CHSW work explained that if we have a Kähler-Calabi-Yau manifold, then it automatically solves this Hall-Strominger system. So in particular, what's happening when you do this conifold transition is that essentially away from these rational curves that are being contracted, not really much is changing. So in particular, if we start with a manifold that has a solution of the Hall-Strominger system, then you might say that, well, if we do this conifold transition, then at least away from the places where we're doing something which is sort of topologically non-trivial, we're not really doing much. And so there we should at least have an approximate solution of this Hall-Strominger system. So let me draw the picture. So we start with some Calabi-Yau manifold, which has some rational curves. And we contract these to get a space which is now singular. So it has some singularities, something like this. And then we smooth these points out to get a new space, which is going to look like the same space, but where we have smoothed out these points. This maybe. So you see, as long as we look sort of away from these curves, there's not very much happening. These spaces are in fact all sort of diffeomorphic by small diffeomorphism. So here we might expect to have a sort of approximate solution. Well, maybe I should say here. So here we have a solution. So who knows what happens to these singular points, but at least away from these singular points, we should have an approximate solution to the Hall-Strominger system. Okay, so that's not very useful. Some sort of philosophy. On the other hand, we actually know quite well what happens metrically near these, or at least we have some picture for what should happen metrically near this local conifold transition. There was work of Candelas and De La Osa, which essentially uses ODE techniques to construct actually Calabi-Yau metrics on all three of these. So both on this, which go through this conifold transition in sort of a continuous way. So in particular, so these are Kähler-Ricci flat metrics. So in particular, solutions of the Hall-Strominger system on this local model. So in particular, you can view this as saying, well, we have a solution, we have sort of approximate solution away from the singular points. We have a genuine solution, at least model solution on this conifold transition. So maybe we can generate solutions by just gluing these two together somehow. So these Candela-Stilo, I mean, these formulas are not so important, but the point is that these Candela-Stilo symmetrics are really, you can write them down because there's so much symmetry in these situations. So we can write down this Ricci flat metric on the cone. This is a cone type metric, so it looks like a Riemannian cone. And then you can write down metrics on this resolved conifold, which are parametrized by a constant which is roughly proportional to the, well, it's proportional to the square root of the volume of the P1. And then similarly, you can construct metrics on the smooth conifold with a parameter T, which is the smoothing parameter. It's roughly the size of the volume of the S3, which is this zero section of the cotangent bundle. So, and then we also have this sort of continuity. So these metrics, in a sort of metric sense, achieve this conifold transition. So back to this picture, we have these metrics, omega COA, where A is roughly the sort of length of this. So as A goes to 0, these converge. So that means the volume of this P1 is going to 0. They converge to this Riemannian cone metric. And then you can smooth these out by essentially by putting in by ODE methods. You can find some omega COTs that live here on BT, and these also converge back to this cone metric as T goes to 0. So this is a sort of continuous process in the geometric sense. Okay, so the first significant result in this direction regarding this Hall-Strominger system was due to Fu Liao, who showed that the conformally balanced equation could be passed through conifold transition. So that's the first equation in the system. So they proved the following thing. They showed that you could produce balanced metrics, which live on both the small resolution side and the smoothing side, and which solve this balanced. So this balanced equation is the same as the conformally balanced equation. You just do some conformal rescaling. It's not a big deal. And which are sort of continuous in the sense that at least locally near the rational curves, this looks like this Candela-Stilo these Candela-Stilo metrics. So this is achieved by a sort of gluing process. And it says that at least for the balanced equation, this is a good local model for the conifold transition, sort of good geometric local model. So the next thing to do once you have the balanced equation is try to solve the Hermitian-Yang-Mills equation with respect to that balanced metric. So this was done in 2012 by a student of Yao. So he proved that if you have a bundle, a holomorphic vector bundle, which is holomorphically trivial near these rational curves being contracted, then you can solve the Hermitian-Yang-Mills equation through this conifold transition. So this assumption about being holomorphically trivial near the rational curves is a very strong assumption. And it's not really clear if this condition is compatible with the anomaly cancellation equation. Even just topologically, it's not clear that it's compatible with the anomaly cancellation equation. And furthermore, so the most natural bundle, so that's sort of what I was explaining when I was talking about the CHSW work, is that the most natural bundle to use in some sense is the holomorphic tangent bundle. It's certainly a bundle that you always have, and it automatically satisfies this the topological there's no topological obstruction to solve in the anomaly cancellation equation for the holomorphic tangent bundle. But this holomorphic tangent bundle is certainly not holomorphically trivial near the rational curves. So Chuan's theorem doesn't apply to this holomorphic tangent bundle. So that's what we did recently. So if you have what we showed is that if you have a conifold transition, and you consider these balanced metrics produced by Fu-Li-Yao, then there are Hermitian metrics HA on the holomorphic tangent bundle of M and HT on the holomorphic tangent bundle of the smoothing, which solve the Hermitian-Yang-Mills equation and which are sort of continuous through this process. So this says that 2 out of the 3 equations in the Hall-Strominger system can be solved simultaneously. So we're only the only thing left to do is solve the anomaly cancellation equation. And actually, from the construction, the metrics that we produce, they sort of approximately solve this anomaly cancellation equation. So in the future, we hope to promote these solutions to solutions of the full Hall-Strominger system. Right, so how is this done? Well, it's done by trying to implement this sort of picture that I described earlier, where we should imagine that we have 2 pieces of the manifold, one which is where there's sort of not much happening away from the rational curves, and a piece which is where we sort of have this Candela-Stillorosa model for a solution of the Hall-Strominger system. So the first step is so these first Hermitian metrics exist by the Li-Yao extension of the Donaldson-Uhlenbeck-Yao theorem. So the first thing to do is to prove that there's a limit of these metrics as you converge to the singular space. So that's done by proving estimates. And now this metric H0, so this lives on this singular space with these kind of ordinary double point singularities, but it solves this solves the Hermitian-Yang-Mills equation on the singular point, on the singular space. And now the next thing, the sort of main input is to say, well, if you have a solution of this equation, well, we have the Candela-Stillorosa metric, which is also a solution of this equation near the conifold points, right? So that means we have 2 solutions of the same equation. You might want to say that they're the same, but they're not going to be exactly the same. But you can say that H0 looks like the Candela-Stillorosa metric plus a small perturbation, which converges to 0 as you go towards the cone point. So that's a sort of key result, is to say that this metric H0, which is produced by this sort of existence result, actually converges to the Candela-Stillorosa metric near the singular point, near all the singular points at a quantitative rate. So this is a quantitative uniqueness of tangent cones result. So now once we know that we have a solution which is very close to the Candela-Stillorosa metric near the singular points, now we can do a gluing. So we have a picture that looks like this. We have a singular manifold with a metric which looks something like this. So H0 is approximately this Candela-Stillorosa metric here. We have a smoothed out manifold, XT, and there's a diffeomorphism basically from any region that looks like this. So you can just flow by a vector field. There's a diffeomorphism, which allows us to put H0 basically outside of any region that doesn't contain the vanishing cycle. And now we can put this omega CH0T here. And we have an estimate that says that on this sort of overlap region from this quantitative convergence theorem, we know that omega CO minus, this is sort of small, and improves, so it gets much smaller as t goes to 0. Okay, so and that's the sort of key input for a gluing theorem. So the problem now is just to make sure that we have essentially an approximate solution with small error, and the theorem then follows from a singular perturbation problem, which is solved by a fixed point technique. So in the last 5 minutes, maybe I'll just try to say something about these type 2A, type 2B theories. So as I mentioned earlier, these Calabi-Yau or Ricci flat Kähler metrics are also solutions of the equations of motion for non-Kähler or for Kähler Calabi-Yaus. And then there are these solutions have these equations of motion have generalizations to non-Kähler Calabi-Yau. So as in the case of the heterotic string, these systems are the existence of theories. The existence theory for solutions to these equations is an active area of research, but it's not fully understood. And these type 2A B theories are a little bit different than the heterotic string in the sense that they have branes, and a lot of the study is more about the branes rather than the equations of motion. And these branes are sort of important because they're supposed to be the progenitors of particles in the string theory. So in the type 2A case, these supersymmetric cycles or A branes are holomorphic curves. And in the type 2B case, these B branes are called special Lagrangians. So special Lagrangians, maybe I'll just write this quickly. Special Lagrangians are half-dimensional manifolds. So in a 2n dimensional manifold, they have half the dimension, and they're Lagrangian. So they annihilate this Hermitian form, and they're special Lagrangian in the sense that they're calibrated by the holomorphic volume form. So in each of these type 2A and type 2B theories, a sort of important invariant is the count of the branes. So in type 2A theory, you count holomorphic rational curves. Type 2B theory, you maybe count special Lagrangian spheres. So maybe those things that's not such a well-posed problem at the moment. But it's useful to point out that something strange happens when you do this conifold transition. Because remember, I mentioned that you delete a two-sphere. So you're removing a rational curve, and you're introducing you're adding a Lagrangian, in fact, a special Lagrangian three-sphere. So these counts are changing. So the count in the A model, right, which is counts holomorphic rational curves, decreases by 1, and the count in the B model increases by 1. And in fact, so in this local model, of course, you lose an A brane, but you gain a B brane, right? So anyways, the total number of A plus B branes is constant. So work which will appear on the archive on Monday, I think. We proved that this local picture is actually globally accurate. So in particular, if you have a conifold transition, even if you're passing from Kähler to non-Kähler, every time you remove a holomorphic two-sphere, you gain a special Lagrangian three-sphere in the smoothed outside, even in the sort of non-Kähler case. And these special Lagrangian three-spheres are rigid in the fact that they don't admit special Lagrangian deformations. So this is maybe not obvious because the deformation theory of special Lagrangians in non-symplectic manifolds is not purely topological. Yeah, so maybe I'd just end with a couple of comments, which is just that these equations of string theory give sort of natural geometric equations for studying complex Calabi-Yau manifolds. And understanding how these equations interact with conifold transitions, essentially any question you could ask about things which should be invariant under conifold transitions is probably not so well understood at the moment. And anything you can say is going to shed light both on this vacuum degeneracy problem and on Reed's fantasy. The most sort of pressing problems, I think, are in the non-Kähler world because we understand the Kähler world so well. And furthermore, if you believe Reed's fantasy, then somehow these non-Kähler manifolds should be the sort of bulk, and these Kähler manifolds should be some sort of chaotic boundary. But really, the part that we understand the best should be viewed as a sort of very small subset of the things that we don't understand. So this is an interesting area. If you're interested, I encourage you to join the fight. So I'll stop there. Thanks very much.
Thank you very much for the nice talk. We have time for questions, of course, and if you have a question, please just unmute yourself or write in the chat and I'll relay the question, or perhaps Tristan can read them.
I have a question. So where you were discussing the smoothing of Conifold, it was all a local discussion, but when you have your Calabi-Yau or you contract this -1 curve, and are there obstruction to do the smoothing globally? Or?
Yeah, and that's exactly this Friedman's theorem, which is that you need that the sum of the classes generated let me just write it down. So you need that the sum, if you contract these rational curves, these should be 0 in H2 MR. So there should be some linear relationship among them for these lambda i's being non-zero. So that's the only obstruction. That's what Friedman's theorem says. So it's sort of if and only if.
Thank you. Anyone else? I see that Pierre-Alexandre Maillot has a question. You can go ahead, Pierre-Alexandre.
So could you say a word about this equality of counts? The thing about special Lagrangians and on the other side, the holomorphic curves?
Yeah, so so actually it turns out that the count is not, the local picture is maybe a little misleading. So the actual count, the way it works is that the number of nodes is equal to the number of curves contracted, number of rational curves. Sorry, I should say not the number of rational curves, but the distinct classes, homology classes of rational curves contracted. Because of course, this condition doesn't give you any information on how many distinct rational, how many distinct homology classes there are, and plus the number of special Lagrangian three spheres created. So this is what happens in the global case, that actually this local picture is a little bit misleading. So then, yeah, so that's somehow the number of nodes, which is exactly equal to would be n in this if you take this formula, it would be n. It's going to be somehow related to because there's some global relations in homology, I guess, amongst the Lagrangian three spheres that you create.
Okay, thank you.
Thank you. I have a very naive question myself. You mentioned that Reed's fantasy could help to salvage string theory from not being able to make predictions. Can you comment on this? How it could help?
Yeah, so I think, I mean, I think, right. Well, I think at least it would tell you that if you believe that and this is sort of understood in some cases. So I think there was some work of Strominger and maybe Morrison and around the time that this was all happening, which says that actually if you for like, I think this is for type 2A and type 2B theories, that as you go through this singular transition, actually the sort of physics part that you care about, so the conformal field theory, is actually totally well behaved. So somehow, even though there's a sort of singular geometric transition, if the conformal field theory is well behaved and this moduli space could be connected, then somehow you would have sort of a contractible space of conformal field theory. So there would be I mean, you could imagine that this would allow you to say that actually, despite the fact that you have all these different vacua, they're really not predicting any different physics.
Yeah. Okay. Thank you. So in some sense, some predictions would be preserved by these transformations.
That's right. Yeah.
Okay, thank you. Anyone else wants to ask a question or comment on something? If not, I would like to thank Tristan again for his talk, and also to congratulate him for the André-Aisenstadt Prize. Congratulations, and thank you very much for giving this talk.
Thank you.